Hello, class. I hope you're having a good night tonight. Um, I regret that the video from my session last night with the few who were in the blended session, uh, the video didn't work out. I recorded, but I didn't have any sound, so I discovered later. So here it's Thursday night. It's been a busy week, but I wanted to do at least a short video covering maybe the most important topic we talked about last night. And most of this you should be able to get from the reading anyway. But I just thought it would be nice to tag up with you here and make a short video. Let you know I'm still here. If you have any trouble with the homework, be sure and reach out to me. I watch your progress pretty much daily on Connect. So, I see some are kind of more aggressive with the homework than others, but my hope is that many of you will have a successful ending to this course. We're not too far away from the second exam, so don't grow weary in well-doing. We're on the cusp of I guess, a holiday break here as I make this recording, but I would strongly recommend that you spend some time with your book and email me over the break if you have any questions. So this is a graduate level class, so you can take the week off if you want. But on the other hand, I think the smart students will spend a little time every day on this material because, we're just a couple of weeks away from finishing. So be that as it may, I want to talk a little bit about the theory in chapter 4. Most folks told me last night, my perception was, at any rate, that chapter 6 and even 7 were a lot easier to read than chapters 4 and 5. So I just want to make some conceptual remarks regarding chapters 4 and 5. Chapter 4 deals with rational behavior on the part of consumers. So we're looking at consumer behavior. Chapter 5, we're looking at producer behavior. What's smart producer behavior? And so Unit 2, since it begins with Chapter 4, by the way, because the first 3 chapters were on Unit 1, and we deferred Chapter 4 to Unit 2, I thought it would be good for us to talk just a little bit about Chapter 4, some things I would like for you to understand in the way of concept. So let's go to the doc cam here, if we can. Let's see, that should be right here. And so in Chapter 4, we deal with the theory of individual behavior, in particular for consumers. And so there's a set of, under consumer behavior here on page 104, at least in my text, there's a set of properties that your book begins to deduce here. Sometimes we call these axioms of consumer preference. So we're kind of in consumer preference theory here. How do consumers behave? And we assume here in our discussion that there's a set of properties that consumers, if they're rational, will adhere to. The first one here is called the completeness property. And it says for any 2 bundles, say A and B, either A is preferred to B, that's what this little symbol means, A is preferred to B, or B is preferred to A, or A is equivalent to B. Equivalent in the sense that the 2 bundles would provide the same utility or satisfaction to the consumer. So we use the word complete here. This is called the completeness axiom. The idea is that there's never any incomplete relationship between 2 bundles of goods. So let's make this simple here, just a second. What we mean is that, obviously in the real world, when you go to the grocery store, what have you, you choose from many goods to consume from, but we got to start somewhere. So we're going to assume a 2-good model here, good X and Y. X may be apples. I'm not very creative here tonight. Apples, and then Y would be oranges. And so what we say that here with the completeness axiom is you can compare any 2 bundles of apples and oranges. So perhaps you've got 10 pounds. Let's measure oranges in pounds. So you have 10 pounds of oranges and 2 pounds of apples. maybe every week you go to the grocery store, and one week you purchase out of your income uh, 10 pounds of apples and 2 pounds of oranges. So that's how we determine this position here in the XY system here. These would be the coordinates 2 and 10. Well, maybe the next week then you go and you purchase 8 pounds of apples and 3 pounds of oranges. Okay, just saying here. And well, that's a different consumption bundle, right? And what we say with a completeness axiom here is that you can always compare two bundles. So either, let's see here, here we go. Either the two bundles are, say over here, equivalent in the sense that they deliver the same amount of satisfaction or utility to the consumer, or one is preferred to the other. That's the completeness axiom. There's a relationship between any two bundles of goods that you might construct. So in this case here, what I'm going to do here is I'm going to say for the moment that these two bundles deliver the same satisfaction to the consumer. They like apples and oranges. Some weeks they may get a bunch of oranges and a few apples. Another week or two, they may get a bunch of apples and a few oranges. But at any rate, these two bundles every week, when they go to the grocery store, first day of the week, they'll get bundles. And if they get one of these two bundles here, then those will deliver the same level of satisfaction. So we would say that those two bundles are on the same indifference curve. So I use the letter I here for indifference curve. And the indifference curve traces out all the bundles that provide the same amount of utility or satisfaction. And so we see here, for instance, that, if the consumer goes to the grocery store and they thought they were going to buy a bunch of apples, but instead there aren't very many apples on the store shelf. So instead, they get a few, I say a bunch of oranges. I'm sorry, oranges is this way. So instead of buying 10 pounds of oranges, they buy 3 pounds of oranges. Then they'll compensate for that by buying a few extra apples and have the same satisfaction or utility. I'm going to put another consumption bundle out here, bundle C, that you'll notice here has the same number of oranges as bundle A and the same number of apples as bundle B. This particular consumption bundle would have to be on a higher indifference curve. I'll call this I2. I1 and I2, these are two different curves here. One is associated with a higher level of satisfaction. And we know that the consumer would prefer to have 10 oranges and 10 apples as opposed to, say, 10 oranges and 2 apples because of another axiom here of consumer preference. And I believe this is axiom number 2. It says more is better. More is always better. So these are goods here. So if you compared these two bundles here, this one's preferred this because C is like A in every respect. That is, it has the same number of oranges, but alas, it has more apples. So C is preferred to A. But also C is preferred to B because while it has the same number of apples, C has more oranges. So we see that C is preferred to both A and B. So this is called the more is better axiom here, if you will. And it's something that just characterizes what a good is. By definition, a good is something you want more of. Yeah, so that's the more is better principle. The third property here is called the diminishing marginal rate of substitution. As a consumer obtains more of a good, X, the amount of good Y he or she is willing to give up to obtain another unit of good X decreases. So in other words, say you're at point A here and you're consuming 2 apples in a week, and you say, well, I'd like to have 6 more apples in this next week. Well, you would give up, it looks like 7 oranges, right? Because if you want to move from consumption bundle A to B, have the same level of satisfaction by gaining 6 apples, then you're going to offset that by giving up 7 pounds of oranges. So we would say that initially, at any rate, from A to B, from A to B, you would substitute, okay? You would substitute 7 pounds of oranges, 7 oranges, for 6 apples. So I forgot the word for here, but for 6 apples. Okay, so this is called the marginal rate of substitution. So we would say the marginal rate of substitution is 7 oranges for 6 apples. And what you have here basically is a ratio, if you will, that gives you the slope of the line that joins consumption bundle A and B. The slope of that line is the rise over the run. And what we're saying is that the marginal rate of substitution is the slope of this line. It connects those 2 points. And so what you see is that if you consume increasingly large amounts of, say, apples, then the marginal rate of substitution is going to decrease. So, if I want to go from 8 apples and maybe consume next week another 6 on top of that, that would be going from 8 to 14. I'm going to have to squeeze that in here, but this is 14 apples. Then I'll call that consumption bundle D because I already have a C up here. But the marginal rate of substitution now would be the slope of this, what we call a secant line, a line that cuts the curve at 2 points. And so this line here has a smaller slope than this line. So the marginal rate of substitution is going to decrease as we consume more and more X. Okay, that's the reason. First off, let me just say that this is a real world phenomenon. Okay, I don't know what 7 divided by 6 is. What is 7? It's 1 point. Let's see here. Reaching for my calculator. I didn't do this ahead of time, but it was like 1.16 or something. But 7 divided by 6 is 1.16. Okay, I should have 1.167 oranges per apple. Okay, per apple. That is the slope of this first secant line. That's the marginal rate of substitution going from A to B. But that's going to decrease. That slope is smaller as we consume more X. You see the first few apples, if you measure the good on the X-axis here, you can tell how much you would give up in the way of a good on the Y-axis to acquire additional units on the X-axis by looking at the marginal rate of substitution. In this range here, kind of on average, you would give up 1.16 oranges to get an additional apple. That's the slope of this line. To get apples beyond the 8th apple in a week, you would give up fewer oranges. So the first few apples are worth more to you than the apples that come after that. This is called diminishing marginal rate of substitution. This is a real world phenomena here. And I like to talk in class sometimes about eating pancakes for breakfast on a Saturday morning. You always have to have a time frame, first off, okay? So when I talk about pancakes, just imagine for a moment. We all know the first pancake is better than the second, and the second's better than the third. You put syrup on that first pancake, so boy, it tastes good. The second one's pretty good. Gosh, that third one, maybe you're starting to get full. You're experiencing diminishing marginal rate of substitution. You give up money to get your pancakes. So imagine for a moment you bought your pancakes one at a time on a plate here. So at any rate, the first pancake, I guess we'd stack them this way. If you ate it, that first pancake, you would pay more for this one than the one that the waitress would bring to you after you've eaten the first pancake. I guess if you eat this one, it disappears. So this one shows up on the bottom. But the point is, the first pancake is worth more to you than the second, and the second's worth more to you than the third. This is just something that we observe always happens when you consume goods in a finite period of time. Now, if you extended this out over a year, okay, the second pancake's just as good as the first pancake. If you're eating your 2 pancakes over the course of a year, you eat one in January, one in August, okay, it kind of nullifies the diminishing rate of substitution effect. What we're saying here, though, is if within a reasonable finite period of time, if you uh, consume increasingly large numbers of a particular good, like apples, then those apples will be worth less and less to you as you consume more and more of them. You'd be willing to give up less to acquire an additional unit of the good, say apples. So you give up a lot of oranges to get the first few apples, not so many oranges here to get the next group of apples, and so forth. So that is diminishing marginal rate of substitution. Now, why is that important? We recognize it in the real world and so forth. But what's important about that is that it means that these indifference curves that we're looking at here have to be convex. They have to be like this. They cannot be concave down or so forth. And they approach the axis asymptotically. But because of diminishing marginal rate of substitution, as you trace an indifference curve out, say from left to right, this secant line that joins adjacent consumption bundles would have to rotate, because again, uh, additional units of the good that we would measure on the horizontal axis would come at a decreasing value to the consumer on the margin. Okay, now you get the same thing for y. You can reflect this graph this way if you want. It's always the case that the slope of the secant line is the marginal cost, if you will, or marginal utility, I guess. I'm sorry, marginal utility of the good measured on the x-axis. So whether you look at the graph this way, or if we had put oranges on the horizontal axis and apples on the vertical axis, it doesn't really matter. As you consume more apples or you consume more oranges, you're going to experience diminishing marginal rate of substitution. Those successively large units of either good are going to be worth less and less to the consumer. Okay, so that's important again, real world, because it makes then these indifference curves convex, shaped out like this. So we've got a lot of structure here when we start talking about consumer behavior. As you go more to the north and east in this diagram, that is, if you take a consumption bundle and add more of both goods, then you have to be moving from a low level of utility to a higher level of utility. So you would be moving from an indifference curve like this one to this one, and so forth. Transitivity is another property of indifference or bundles, three bundles, A, B, and C. It's simply saying that with transitivity, if A is preferred to B and B is preferred to C, then A is preferred to C. Okay, this is transitivity. Or if A is equivalent to B and B delivers the same satisfaction as C, then A is equivalent to C. Okay, I want to focus just a little bit, not get too theoretical. I'm going to do my best here, but I want to explain one concept back here on marginal rate of substitution again. Let's just think about this a second. Between these 2 points, A and B, let me draw this again, and let's think about in a little more depth how the marginal rate of substitution is related to the utility function itself, the function that tells us how much satisfaction we derive from these two consumption bundles, or any consumption bundles we measure in this system. The marginal rate of substitution, as I said, is the slope of this line here. So what is the slope of a line? The slope is delta y over delta x. Okay, so I'm going to put a delta y here and a delta x. And so what I'm saying is that you would substitute units of y to get more units of x at the rate given by the slope of this line. That's the marginal rate of substitution. That's delta y over delta x. And so these two consumption bundles are on a particular indifference curve. Now, I want you to think for a moment of this problem we're looking at in three dimensions, okay? I don't want to stretch this too much. I don't want to make this too theoretical. But we're measuring goods on each axis. Maybe this, again, is apples, and this is oranges. It just doesn't really matter. It could be consumer goods and non-consumer goods, capital goods, whatever. However you want to, could be food and non-food goods that you consume in a period of time. You can take your expenditures and divide it in two groups and kind of think of your expenditures in that manner if you want. But at any rate, I want you to think for a moment about adding a third axis. Okay, so you can't really do that on a sheet of paper. So I've got my ink pen here, and I've got it coming at us here from the table. And so what we're measuring in this direction here, in the axis that's coming to you, is we're measuring utility. Okay. Now I hope the analogy I want to make here will make this real world to us. If you've ever seen a topographical map, maybe something that looks like this, okay? Have you ever seen, this is a map here, and you've seen a topographical map, and you might have some little numbers here, 100, and this might say 110, and this might say 120. I don't know if you can see that or not. I probably should have drawn this a little bigger. But these are called contour lines, and the numbers associated with them are elevations, say above sea level. So this would be 100 feet above sea level, 110 and 120. And maybe this is the state, maybe that's the state of Kansas, okay? Looks kind of like Kansas a little bit. And maybe you got some other contour lines over here, at different elevations. Maybe this is 90 and 80. I know Kansas is much higher than this. It's around 700 feet above sea level. But anyway, it doesn't matter. You could tell in a two-dimensional map what you're looking at with respect to this third axis here that measures elevation. I mean, I think you should see that this is a hill, right? That all of these points here in the state of Kansas, kind of in the floor of our 3D model, are at an altitude of 100 feet. These are at 110 feet and 120 and so forth. So you got a hill that's coming up here. And maybe over here you got kind of a gully over here, especially if this went back up to 90. So you might have a gully over here. Hopefully everybody spent a little time and looked at a map like this or thought about this, surely. Okay. So what we're representing is a third dimension in a two-dimensional diagram. This third dimension is the only way we can represent it on a sheet of paper, like we want to represent a third dimension here on this sheet of paper where that dimension represents utility instead of elevation, as we have here, height above sea level. Let's use that third dimension here to represent utility. Now, we can say that a measure of utility maybe is a util, okay, for a moment. So this would be feet above sea level, okay? Whereas utility might be measured in utils instead of feet. But at any rate, we could picture that again as a vertical displacement off the page. So these two consumption bundles would deliver the same utils, number of utils, but a utility function, a function that would obey have this behavior that more of each good is better than less, would be a three-dimensional function that would be a hill, kind of like coming up like this. Because as you get more X and Y, you're going to have a greater distance vertically toward the camera here that would represent satisfaction or utility. So the indifference curves would have to have this kind of shape to them here. You got I here, you got maybe I1, I2, and I3. This one would have a set of consumption bundles at a higher utility than these and so forth, because what these are contour lines corresponding to this function. It looks like a hill that goes higher and higher as you go to the right and up. Well, big deal, right? Okay. Well, what I want us to think about here in just a moment is another way of expressing the marginal rate of substitution that's going to be very handy to us, especially as we get, I believe, into chapter 8. And I want us to think about these as being contour lines like we have on a map here. So these are at the same elevation. And you want to start at A and you want to start at B. Maybe you have a person here and another person here, and you want them to meet at some point on the hill. Okay, so I'll tell you what, let me put this point right here, C again. So here's another utility function. Whoops, they never do cross. So there you go. So at any rate, if you go from A to C, or from B to C, since you start at the same level and you end at the same level, you're going to climb the same number of feet vertically. That is, you're going to increase utility from A to C by the same amount that you would increase utility from B to C. Okay, so the amount by which you increase utility going from A to C is delta X times the slope of the hill in this direction. And the amount of utility you would experience an increase in going from B to C would be delta Y times the slope of the hill in this direction. I mean, this is delta X, just as this is delta X, and this is delta Y, just as this is delta Y. So, I mean, I guess in words, I would say that the change in height is equal to the lateral change, okay? However many feet you walk to the east times the slope of the hill in the east direction. And however many feet you climb as you move to the north is the number of feet you walk to the north times the slope of the hill in the north direction. I think that should make sense to us. So what we're saying is that those two vertical displacements are the same. So for instance, here, going back here, if I take delta X times the slope of the hill in the X direction, going from uh, A to C, delta X times the slope of the hill in the X direction from A to C, this slope is called the marginal utility of X. Okay, that's the term, that's the word we use to find the slope of a function like this. This is telling you how utility changes as we change this variable here. And we've looked at this before. This is actually a partial derivative. It's a derivative of the utility function with respect to x. But I'm just going to leave it like that for a moment. Likewise here, the vertical displacement that you would experience when you go from B to C is delta y, the lateral distance here, the distance in the plane, times the marginal utility of y. Okay, so the marginal utility of oranges. How much additional satisfaction do you get as you consume each additional orange? That would be the slope of this curve or this surface in the y direction because we're measuring oranges in the y direction. I hope this isn't too abstract, okay? But the reason I'm mentioning this is going to give us something we can work with because I've expressed the marginal rate of substitution over here as delta y over delta x. So I'm going to re-express delta y over delta x as the ratio of these two marginal utilities. It's the marginal utility of x or the marginal utility of y. Okay, so the marginal rate of substitution is not only this expression here, okay, but it's also equal to the ratio of the marginal utilities. Marginal utility of x divided by the marginal utility of y. And these are just partial derivatives. If you have a utility function like a Cobb-Douglas utility function that I mentioned in a previous video, you can find each of these marginal utilities by taking the derivative. Really, it's a partial derivative of the utility function with respect to the x variable and the y variable, respectively. I'm just going to mention that here because this is one half of the story for consumer behavior. I want to lay this to the side for a moment. The marginal rate of substitution is equal to the ratio of the marginal utilities. The other thing I want to talk about, and this is something you do have problems on for sure, is this concept of budget line. A budget line. A budget line is a representation of all the consumption bundles you can purchase on a fixed income. So suppose M is your income. Maybe it's $60 a week. We use M for some reason. That means income in economics. Piece of A here, I'll use a capital A from a subscript. This is the price of apples. So suppose price of apples here. I'll tell you what, I want to stick with X and Y, okay? But piece of X is $4 a pound. And this is the price of apples. Okay, so we'll just have to remember we used apples on the x-axis just a moment ago. Piece of y is, say, $3. per pound. This would be the price of oranges. So we're measuring oranges on the horizontal axis. At any rate, X and Y would represent the quantity of apples and oranges you can purchase in a week on a $60 income, given these prices. Okay, and that can be represented by a line that would be of this form. M, your income, is equal to the price of apples times the number of pounds of apples plus the price of oranges times the number of pounds of oranges you would consume in a week or would purchase in a week. Okay, so income is 60. Okay, the price of apples is $4. So $4 times X plus $3 times Y is a linear equation here that represents a line in two space called the budget line. So it's going to be a line that looks like, I'll just rough it out here for a moment. Again, X is apples, Y is oranges. And in particular, we can find these 2 points. If you got 2 points, you can sketch a line easily enough. You can find those 2 points by letting one of the variables be 0 and solving for the other. These are called intercepts. For instance, if I let X be 0, if X is 0, this term drops out, and 60 is equal to 3Y, so it sounds like Y is equal to 20. 3 times 20 is 60. So I'll let one variable be 0, solve for the other. Here, if I let Y be 0, this term drops out. I get 60 over 4 for X, and that sounds like 15. So these 2 points, 0, 20, 0, 20 is X is 0, so you're on the vertical axis and you're up here at 20. And 15, 0, Y is 0, but X is 15, you're down here on the X-axis. These 2 points here are the intercepts. And in general, you can find the intercepts this way. You take your income and divide by the price along that axis. This is the income, $60. I mean, how did we get Y? You take $60 and divide by the price of Y. So take the income and divide by the price of Y, gives you the Y-intercept. Here, the income divided by the price of X gives you the X-intercept. This is the budget line, and you can consume any bundle of goods on this line for $60. You can also consume under any bundle under that line if you want, but this represents the maximum consumption bundles. The ones that if you're spending all of your money, you will consume some bundle on this line here. Now, if your income goes up, say from $60 to $120, this line would shift out. I think you see if N is increased, this line would shift out in this fashion here. Also, if the price of one of these goods, say the price of apples goes up from $4 to $8, okay, from $4 to $8. I'm getting a little static here on my, hang on, I may have a connection problem. Hopefully that will fix it. I don't need another technical difficulty here today. Something's happening here. Okay, so at any rate, if the price of apples doubles, say, then I think you'll see that this budget line is going to rotate this way. It's going to go in like this. Okay, because now you have a $60 income over $8. Okay, instead of $4 per pound of apples, it would be $8 per pound. So if you took 60 and divided by 8, then you get 7.5, I believe. So that would be this point right here. So if the price of one of the goods goes up, the budget line swings in like this. If the price goes decreases, the budget line is going to swing out. Okay, I think I got my camera back. Okay, so either one of these lines, the one we started with, represents all these consumption bundles you can afford on $60 a week if these indeed are your 2 prices. So let's stay with this one for a moment. And you see that you could consume this consumption bundle that's the midpoint of that segment. What would that be? Okay, if you go midpoint from 0 to 20, this would have 10 oranges and last 7.5 apples. You could also purchase at these prices $4 and $3 for apples and oranges respectively. You could purchase 7.5 pounds of apples and 10 pounds of oranges. Just try that if you want. Put a 7.5 in here and a 10 here, and you're going to see that that's equal to $60. Okay, so I want you to understand budget lines and so forth and what those are. This is the other half of the story that we're going to put together here in a minute. But one other thing I want you to understand is that just basically a formula here, if you will, for the slope of the budget line. The slope of the budget line, whether you're talking this one or what have you, can be obtained by looking at this general form for a budget line and writing that in slope intercept form. Maybe you recall this from school. Remember, hopefully, everybody's had algebra. Okay, I've got to assume that everybody's done all this. We're going to write this formula right up here in the form y equals mx plus b. Okay, so we're going to write this formula. There's a general form for a budget line in what's called the slope-intercept formula. So we do that by solving for y, okay? Because you have y isolated on the right. So I'm going to isolate my y term on one side. So I think for a moment, I'll bring this over to the left. So this is a negative piece of x plus m equals p sub y, y, okay? And so I'll have the y by itself if I divide through by p sub y. So this is a negative p sub x over p sub y x plus m over p sub y. Now this is in this form. Hope you see that. I got the y by itself. I guess I could have written it this way. Y equals a negative p sub x over p sub y. X plus m over p sub y. This expression right here is the slope. It's the coefficient in front of the x term. Okay, and maybe you recall that the constant term over here would be the vertical intercept. We call it the y-intercept. And so what we're saying here is something, one of these things we already noted. The y-intercept indeed is m over p sub y. The income over the price of the good on the y-axis indeed is the intercept. Okay, so this is the y-intercept. And can't spell, but anyway, and this is the slope. Okay, this is the slope. Now, what we really care about is the magnitude of the slope here. And I'm saying here that the magnitude of the slope for the budget line here, either budget line, is always the ratio of the prices. This thing right here, the slope of the budget line, has a absolute value equal to p sub x over p sub y. Big deal, right? Well, I want to go back here and use that because when we talk about a consumer being in equilibrium, we mean that they're going to consume a bundle of goods on their budget line that puts them on the highest indifference curve. So here's an indifference curve here that just touches the budget line. Now there are other indifference curves like this one here. This is good on the y-axis and good on the x-axis. But you have higher utility experienced on this indifference curve than on this one here. Okay, I mean, this is I sub 0 or something. Because this one is to the right. It's above and to the right of this one. So this is going to connect bundles that would deliver more satisfaction to the consumer. So you want to get on the highest indifference curve. And when you do, then the slope of the indifference curve equals the slope of the budget line. And this is the slope of the budget line. And we just now found what the slope of the indifference curve is that would pass through that. Recall that? We said that the marginal rate of substitution, which is the slope of the indifference curve, is the ratio of the marginal utilities. So I'm going to set the slope of the budget line equal to the slope of the indifference curve, which is the marginal rate of substitution, which is given by the ratio of the marginal utilities. Okay, so that's why I went through this discussion of expressing the slope of an indifference curve by looking at the utility function. So it's the ratio of the marginal utilities. If I set that equal to the slope of the budget line, then I have an equation like this right here that establishes what's called consumer equilibrium. You'll have consumer equilibrium at this point. Consumer equilibrium. Another way of writing this is to cross multiply and write it in the following way. Okay, I could cross multiply and I hope you see I could write this as marginal utility of X over the price of X equals the marginal utility of Y over the price of Y. Or sometimes we'll put the X on the left and the Y on the right, but it doesn't really matter. Consumer equilibrium is achieved when I have the same ratio of marginal utility to price across both goods. This is called consumer equilibrium. The consumer is in equilibrium at this point. The consumer is enjoying maximum satisfaction with this bundle. Now, they can afford this bundle over here, but they're better off with this one. Okay? They can afford any bundle on the budget line, but this is the one that delivers the most satisfaction to the consumer. Suppose for a moment we were over here, okay? This one would have a marginal rate of substitution greater than the slope of the budget line, okay? I mean, what if that were the case? In other words, if, suppose for a moment, that the slope of the marginal rate of substitution, were greater than, just suppose, the slope of the budget line. The slope of the budget line is p sub x over p sub y. Okay, so in other words, if we were here, the slope of the indifference curve going through that consumption bundle, which is the marginal rate of substitution, is greater than, it's steeper there, right, than the slope of the budget line. Now, the marginal rate of substitution, recall, is this thing right here. So what we'd be saying is that the marginal utility of x over the marginal utility of y is greater than p sub x over p sub y. I'd no longer be satisfying this condition, or this is the one here that most people remember. And I want to encourage you to remember it in this form. This you might call the bang per buck rule. Okay, you want to get the same bang per buck across all the goods you consume. In one of the videos I do in my principles level class, you want to go back and you want to watch that and look at how we try to satisfy what's called the rational spending rule. That's another term for this, by equating bang per buck across all goods until we exhaust our income. But at any rate, suppose we're over here, the marginal rate of substitution will be greater than the price ratio, and this is the marginal rate of substitution. So you're going to see, if you rearrange your terms here just a second, that this is certainly not satisfied. Let me try to write it in this form. Basically, what we would be saying is the marginal rate, a marginal utility of x, or the price of x, is greater than the marginal utility of y over the price of y. So I'm just saying that if we're away from consumer equilibrium, where the two slopes are equal, we might be at a point like this. And if that's the case, then you've got a situation like this. It's not equal. Now, what you want to do is, if this is what you experienced this week, then next week you want to reallocate your spending in such a way that you'll derive more satisfaction on your income, say, of $60. So the question I'll put to you here is this: to increase, say in the next period of time, increase utility across all goods consumed, we need to do something here. We need to purchase and consume more of one of these goods and less of the other. So you only have $60. So if you buy more apples, you got to do with fewer oranges. If you want to buy more oranges, you got to do with fewer apples. So if this is the situation, you're not experiencing maximum utility. So what you want to do here is you want to rearrange your spending, reallocate your spending in the next period of time so that you have an equation here. Now, there's part of this, as a consumer, you have some power over some things you don't. Typically, when you go to the grocery store, you have no power over the price of apples and oranges. You just look at the sign on the shelf and you take these things as given. And so we're going to assume that here in this course, for the remainder of this course, that prices for a consumer are given, okay? But you can affect the marginal utility on the last unit of X and the last unit of Y consumed, oranges or apples and oranges respectively. How do you do that? Well, you appeal to this thing called, and we alluded to this just a moment ago, diminishing marginal utility. diminishing marginal utility. Again, as you consume more and more of a good, you're going to experience on the margin less and less utility. The first pancake delivers more satisfaction than the second more than the third, and so forth. So on the margin, that's the additional unit that you would consume in a period of time, will deliver less satisfaction than the unit before it. So we're going to use that fact here to rearrange our spending so that we will satisfy then what we could call the bang per buck rule, if you want here, bang per buck, or rational spending rule, what have you. I would remember the relationship for consumer equilibrium in this form right here. Okay, we derived it, and your book goes through this a little bit. Look in the appendix as well, they'll derive this. But this is, I think, a more useful form for working problems and so forth. They're equivalent. But anyway, if you want to get equality here in this relationship, when you have an inequality, then you need to drive the fraction on the left down. You have no control over the price. You need to drive the fraction on the right up, but again, you have no control over the denominator price here as well. So you need to drive this down and you need to drive this up. And you can do so if you understand the law of diminishing marginal utility. To drive the marginal utility of good X down, you need to consume what? More X. Consume more X, and then the last unit of X that would be consumed would deliver less marginal utility than before, than the last unit you consumed in the previous week, and consume less Y. If you consume more apples and less oranges, then you'll begin to move this fraction down on the left, this fraction up on the right, and you'll experience more total satisfaction. So this is how we go about trying to establish consumer equilibrium. Now we see that in the diagram here as well. I mean, the problem with us being at this point is that we're not at this point. So how would you go from this point to this point? You go to the right, you take more, you consume more X, and you go down, you consume less Y. So that's what we're saying here. We see it graphically. You also see it algebraically as well. Because of the law of diminishing marginal utility, consume more X and less Y on your $60 income or whatever your income is, and you'll experience greater levels of utility. Okay, so I hope this is helpful in that when you read the chapter and read all the way through the chapter, I would ask that you also read the appendix in chapter 4. I know it's a little theoretical, but you know, this is a pivot chapter, really, even more so than perhaps chapter 5. I wanted to focus on this video there, however, on chapter 4, talk about consumer behavior. With consumer behavior here, you always want to satisfy that bang per buck rule or that rational spending rule, where you equate marginal utility to price over all the goods that you consume. Whether you consume 3 goods, 4 goods, or what have you. You got pizzas, candy bars, whatever it is, you buy all these things. You throw things in the grocery basket. You're actually using this computer up here in a way that you may not fully realize. You're always seeking to establish consumer equilibrium, get the same ratio of marginal utility per price. So you may see a T-bone steak there. You go, wow, that'd be great. You pick it up and you look at the price. So you weigh 2 things out. You weigh the satisfaction that additional unit will give you, consumption. Maybe you'll load the basket up with T-bones. I don't know if they're cheap enough. But you'll make this comparison of the marginal utility to the price. And we just do this intuitively. The brain is an amazing thing. It's a great calculator. It's amazing that you can be driving down the road and you can look in your rearview mirror and you can see a little blank in the traffic coming up on your right-hand side, and you can begin to speed up and merge in that lane. There's some pretty sophisticated mathematics involved in doing that. If you had to program a computer to speed up your car and emerge into an adjacent lane like that, it would be a non-trivial problem. But we just do these things by instinct. So whether you realize it or not, we've whether you think you're a mathematician or not, you're actually solving a relatively complex kind of problem here when you go shopping and you throw things in your shopping cart because you're looking at prices and you're looking at satisfaction simultaneously for each unit you throw in your shopping cart. There is on one of the videos I've made for my principles level class, a problem where we work through obtaining the optimal consumption bundle on a fixed income, where we're continually striving to satisfy this relationship that we just now drew out. So I again want to encourage you to watch the videos I put up from my principles level courses because I think they'll assist you. A lot of this same theory extends to production as well. Here we in chapter 4 have talked about the consumer, and it's just the nature of this course that we don't have 3 hours a week for 15, 16 weeks to talk about this. So you're going to have to, just the way this course is, you're going to have to kind of reach and get some of this in the reading on your own. But when you read chapter 5, I think you're going to see some parallel theory here. Producers also want to satisfy a relationship that's similar to the relationship that consumers want to satisfy. Instead of um, instead of us trying to satisfy a utility function, producers try to uh, obtain profit and profit from a production function. So I think I'll just draw things up right here as far as chapter 4 goes, but chapter 5, I want you to be sure to look at the videos that I have put up there where I talk about these curves in particular. Let me go to the document camera here. This is called a total product curve. Okay, it's always an S-shaped curve like this. It deals with production in the short run, where you have a fixed factor of production. Maybe floor space in the plant is fixed or something like that. But you do have a variable input. So generally labor is a variable input, but capital is fixed. If that's the case, you always have a total product curve that looks something like this. Okay, I know it's kind of roughed out here, but this is total product, units of output, and this is units of variable input, say labor. Initially, as you hire workers, you're going to increase output at an increasing rate. So I want to draw a vertical line right about here. And this total product curve is shooting up at an increasing rate here. It's increasing at an increasing rate. And the reason why this is very typical, and I mentioned this in one of the videos, is say, for instance, you have a plant with 4 workstations and you begin to hire workers. You can hire 1 worker, you can hire 2 workers, and so forth. But it turns out initially, if you double the number of workers that you hire, you'll more than double your output, especially say if you have 4 workstations. I think I mentioned in one of the videos that there's a little factory here that makes baseball bats. You have wood that comes in one door, like hickory. And so you have a saw here that just chops it up. You have a lathe here. Okay. And then you have a finisher here. Okay. You have a finisher, puts a lacquer on there. And then you have shipping over here. Okay. Imagine that for a moment. 4 different workstations. So you could operate that with 1 person, but in a day, they would not, in one day, they would not produce very much output. Maybe they produce 100 bats. The reason they wouldn't produce very much is they're running around between 4 stations. So if you double the number of workers here, guess what? You're going to more than double output. So this might be 300 bats. Instead of 200, it might be 300. Why is that? Why is it? If you double the workforce initially, you'll more than double output. The reason is there's less time between tasks. You begin to specialize. You might have this worker work the left side and this one work the right side. So this one gets real proficient at 2 machines. You don't have to worry about them operating 4 machines. And this one works these 2 on the right. So doubling the input more than doubles the output. This is labor input. What if you double again? So of course you could have 3 workers. I'm just going to put these here for a minute. But let's go to 4 workers, okay, where you double from 2, you go to 4. And if that's the case, then guess what? You can put 1 worker to each machine. You can really specialize then. I'll guarantee you'll more than double the output with 2 workers. So this may be 800, okay? Could very well be. So see how you're increasing at an increasing rate. We could plot these points if we want. This one might be in the middle somewhere. Maybe this is 450 or something like that. Let's see, three, I don't know, maybe it's 500. Okay, say it's 500. But at any rate, what you're seeing is that as you begin to specialize, the total product increases at an increasing rate. It really skyrockets. Now, with a 5th worker, you're going to produce more as well. So if you have a 5th worker, maybe that's 900 bats or something, but you begin to increase at a decreasing rate. A 5th worker will produce more than 4 workers, even in this little factory, because that 5th worker can spell each people off as they take a break and so forth. But if you continue to add workers in this environment, you may continue to add output, but you're going to experience some crowding out. Or that is to say, you're going to have some people with their hands in their pockets because there's only 4 workstations. You put 20 workers in here, you're not using your labor efficiently. And certainly if you put 20,000 in here, they don't have enough room to move around. So the point here is that maybe up to that 4th worker, you're experiencing increasing returns to labor, okay? The marginal product of labor, which is kind of like our marginal utility we read about just a moment ago when we started joining consecutive points on the utility on an indifference curve. You got the same sort of thing here. You want to pay attention to that in the video I'll post. But you can produce more with 4 than with 3, than with 2, than with 1 worker, but you're going to increase your output at an increasing rate. And then you hit this inflection point where 5 workers will produce more than 4, certainly, but not that much more. You don't get that much additional kick from the 5th worker as you did with the 4th worker. So a total product curve is going to be like this. Beyond the inflection point, you're increasing total product at a decreasing rate. So that you kind of have to zoom in to see this here, but this is called a total product curve. So I know I kind of roughed it out there a little bit, but it's kind of an S-shaped curve like this. Okay. Additionally, associated with that is this marginal product curve and average product curves. Be sure and watch the videos from my principles level class, if it's been a while since you've done principles level, to see why these are U-shaped curve. The product curves look like this. This is total product, this is average product, and this is marginal product. And then in the short run, we also have cost curves, and it's these cost curves that are all important to us. All right, so when you read chapter 5, you're going to get to a page here, and I marked on this last night, and it just seemed to be a little easier to go through this last night, but read about the marginal cost curve, the average total cost curve, and the average variable cost curve. This is kind of like the crescendo of chapter 5 when you read about production. I want you to understand what these 3 curves are. They're curves that confront a manufacturer or producer in the short run when there's a fixed factor of production, maybe just so much floor space in the factory or what have you. Like we have here in this little factory that makes baseball bats. We can add workers, but we can't double the size of the factory. And because of that, that's why you have a total product curve that has kind of this shape to it. If you could continue to increase the size of the factory, then this thing could continue to shoot up. Okay, if you had 8 workstations instead of 4 and so forth, if you could double the workstations as you double the employees, then this curve would never begin to be concave down. Hope that makes sense. In the short run, economists define the short run as the length of time in which there's one fixed factor of production. Either the machinery's fixed or the labor's fixed. Typically, it's the machinery or floor space, something like that. Well, if that's the case, then not only are you going to see diminishing marginal product here. We're going to talk about marginal product, the additional product for adding another worker. It goes up, total product goes up, but at a decreasing rate. Eventually, always is going to happen. You're going to see that in the short run. But that's also going to drive the cost of production up in the short run. So if you want to produce a lot of output, the only way to do that is to hire a bunch of workers. You might have to hire that fifth worker, the sixth worker, and so forth. They'll produce more output, but that output will be more costly. Okay, so it makes these three curves here shoot up on the right. So in the video, I'm trying to do several lessons that we would talk about in a standard semester and principles level class, kind of trying to do this in one setting here tonight. But I talk about the marginal cost curve, the average total cost curve, and the average variable cost curve. They're all three U-shaped curves. They're short run cost curves. And the marginal cost curve always goes through the minimum of the average cost curve, whether it's the average total cost or the average variable cost curve. So this is just something you're going to have to get in the reading. I want you to read chapter 5 carefully if you haven't yet. Chapters 4 and 5 are all important. There's a lot of factual stuff in chapter 6 and so forth, 6 and 7. But the theory that you need to grab onto for both consumer behavior in chapter 4 and production theory in chapter 5 will come together in chapter 8, as you're going to see, which is the crescendo chapter of this course. So I encourage you here. It's a fast-paced course. I think ideally this course should be taught in 16 weeks, not 8, but that's just the environment we live in. So I would encourage you over the Thanksgiving break, spend time to read through these chapters. Email me if you got any questions. I'll be checking my email every day, and I'm here to help you to the extent that I can. But alas, a lot of this will require significant work on your part. I'm pretty casual tonight. I'm just in my t-shirt, normally in my summer camp t-shirt where we go help the kids at church camp. So this was really off the cuff tonight, but I hope with my thumbnail sketching here that it will assist you in the reading and getting these concepts down here in chapters 4 and 5. So let me know if you have any questions, and hopefully we'll talk again soon. Have a good evening. Bye-bye.